if let's just say you have a pool of water here, this is water. If you have a pool of water here, and then you have something like a sphere connected to an, say, oscillator. If you switch on the oscillator, it will cause the sphere to move up and down, hitting the water. So when you have a sphere that moves up and down hitting the water, it will start to generate waves. Okay, and the waves will always be circular in nature, by nature. So the waves will be circular, and then it will start to go out. It will spread out. Okay, so this is something that you can normally observe in everyday life. If you take a small sphere or small ball and then you dip it up and down on the water surface, you will see waves being generated, and the waves are normally circular. Okay, so the thing now here that we want to talk about is interference between two different waves. Hence the reason why this subsection is named two source interference patterns. Okay, so what we want to know is what happens when two different waves from two different sources meet each other. Okay, so the most simple example of two source interference is shown by your ripple tank experiment. Okay, ripple tank experiment is meant to show interference between water waves. It's meant to show interference between two sources of water waves. Okay, so what you have here is a ripple tank experiment. All right, so instead of just having one sphere, right now you have two different spheres, and then it's connected to an oscillator or a motor. All right, so what will happen is that the oscillator or motor will cause these two spheres, we call them dippers, to move up and down. So when the two dippers move up and down, each dipper or each sphere will generate its own water waves. Okay, so if this is the first dipper, it will generate its own water waves like this. If you have the second dipper, it will generate its own water wave that looks like this. Okay, so the thing is that this wave and this wave, as they propagate outwards, they will eventually meet. Okay, so when they meet, we're interested to know what happens. What happens is explained by using superposition or interference. Okay, so you see on the diagram here, this is the pattern of the water waves. All right, so the blue colored waves that use the blue colored lines that you see here are representing the wave crest. Okay, so there's source A and source B here lah. All right, so as I mentioned to you, the waves are circular. They will propagate outwards. Source A will have its own waves. Source B will also have its own waves. Okay, at some point or some region, they will tend to overlap. So we are interested to know what is happening. Okay, so the blue colored wave here represents the crest of the waves. The dotted red line represents the trough. Okay, so when the waves from the two sources spread out and overlap, there will be certain specific points where you would have constructive interference and destructive interference. Now, constructive interference, remember I mentioned to you, is where the waves meet in phase. Waves meet in phase, meaning to say crest with crest or trough with trough. Okay, so that will mean that in this diagram here, if I see a solid blue line meeting with another solid blue line, like say for example, here and here, this one here is going to be constructive interference. Similarly, if I see a dotted red line meeting a dotted red line, that means it is trough, meeting a trough. That point would also be constructive interference. Okay, so because you see, if I try to draw for you constructive interference, it generally looks like this. A crest will meet with a crest, a trough would meet with a trough to give you a new wave of even bigger amplitude. Okay, so crest meets crest, trough meets trough. That is constructive interference. The waves are meeting in phase. So here, if you look carefully at the diagrams, when the blue line meets with a blue line, that one is one point of constructive interference. When a dotted red line meets a dotted red line, that is also another point of constructive interference. Okay, so you trace all those points where constructive interference occurs, it will be these points here. 1, 2, 3, 1, 2, 3, 1, 2, and then 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. Okay, so these points here where constructive interference occur will eventually trace out a line like this. Okay, this is your regions of constructive interference. Okay, so as the waterways spread out from the two sources, you will eventually see that there will be certain regions where constructive interference occurs, and similarly, there will be certain regions where destructive interference occurs. All right, so the green colored lines that I've highlighted here with the letter C, labeled with letter C, those are regions of constructive interference, because that's where all the waves always meet in phase. Crest meets a crest, trough meets a trough. Okay, so in between those regions of constructive interference, you would have regions of destructive interference. Now, when you're talking about destructive interference, I mentioned to you that the waves meet out of phase, which in turn means it is crest with trough. So if this one is constructive, destructive is something that looks like this. You again have the two waves. One, you can have something like this, and then something that looks like this. Here you will see that crest meets with trough, crest meets with trough. So this one will in turn give me nothing. Assuming that the amplitudes are the same now, okay? If let's say this is amplitude A, and then this one is also amplitude A, when they meet, they cancel each other off, completely cancel each other off. So you get nothing, okay? So when they meet out of phase, crest meets with trough. That will mean that you expect to see, if a solid blue line meets with a dotted red line, that is where you expect to see destructive interference. Okay, so if you look carefully in the diagram where a solid blue line meets with a red dotted line, that one will always be destructive. That one will be these points here. Okay, if you look carefully later on, I'm just indicating all those little points here for you. Okay, so it is all these little points where you see a solid line meeting a dotted line, which means a crest meets a trough. So this is where destructive interference occurs. So you trace out all the points, they will form this little region here. Okay, this one here is destructive interference. So here, in the case of a ripple tank experiment, which is meant to show interference pattern from two sources or two sources using water waves, you expect to see this pattern. Okay, this little thing here is what we call interference pattern. Okay, you can see certain regions that are constructive. You can see certain regions that are destructive. Okay, this is what we call as interference pattern. Okay, how do you see this in practice? In the case of waterways, when you are constructing interference, you see that the waterways there are a bit higher. In the case where you have destructive interference, you see that the water waves there are almost non-existent. We will say that you see regions of wavy waves, wavy water. You see certain regions where the waves are moving up and down, and certain regions where the waves are not moving at all. It's better to explain it like using a video. Let me just show you the video for ripple tank. This video. Okay, wait. Superposition. Waterways. Okay, let me just open out the video for you to see. Let me share the video with you. Okay, now you should be able to see on your screen right now some sort of animation that is playing. Okay, this is the interference pattern. Okay, this is the interference pattern from a ripple tank. Okay, so you have the two dippers, which is this two here. This is say dipper A. This is a dipper A. This is a dipper B. S here stands for source. Okay, source A, source B. All right. So you have the two dippers that are moving up and down. The two dippers moving up and down will generate waves that are circular that will spread out. Okay, so S1 will have waves that spread out like this. SB will have waves that spread out like this. So just now I mentioned to you, there will be regions where the waves interfere with each other or superpose with each other. So there will be certain regions where constructive interference always occurs because crest always meets with crest, trough always meets with trough, and there will be certain regions where destructive interference occurs, where crest meets with trough. So you have those regions of constructive and destructive interference. So on a ripple tank, how do you see it? Is by what you're seeing here right now. Okay, so let me just erase some stuff here. You will notice that there are certain regions here that seems to be very calm. That one is this one, this one, this one, this one, this one, this one, and this one. Okay, so notice that the lines here that I drawn, the waterways around those lines, along those lines, don't seem to be wavy. They appear to be calm, like there's no waterways at all. This part here is where your destructive interference occurs. But if you look at the region in between the destructive region or in between the calm regions, namely this one, maybe I use green, namely this one. Okay, green is a very bad color to use. Maybe I should use pink. Okay, yeah, namely this one. You will see that you can see those little shadows here, right? the shadows that are moving, this is actually the wave that is moving up and down and then moving outwards. Okay, so this part here you see that is wavy is actually the part where you have constructive interference. Okay, so this little thing that you see using a ripple tank, this is what you're going to see. All right, the regions where you don't see anything, it seems to be calm, that is where destructive interference occurs because no wave is there. But on the regions in between, where you can see waves, and then they seem to be quite large, that is your constructive region. Okay, so this one here is your interference pattern. All right, so when you want to see this little pattern here that is created by a ripple tank, normally what we'll do is this. Usually your ripple tank is this one here. There is a transparent bottom. Okay, your water is contained inside this little container here. Wait, let me just close off the diagram now. Wait. Okay, let me just go back to the little diagram. Okay, right. So for your ripple tank, when you want to see the interference pattern like that is shown inside the animation, what we'll normally tell you is that this little container that contains the water has a transparent bottom. Okay, it has a transparent bottom. Okay, so what you do is that you will put a piece of paper or screen below the container, and then you will use a lamp to shine onto the pool of water. So when light is being shown onto that water, which has an interference pattern, it will form a shadow pattern on the paper or screen below. So if I want to draw a 2D view for you, it looks something like this. This is your ripple tank. This is your dipper. This is your oscillator. This is your oscillator. And then this is your dipper. And then your water is inside here. Okay, this is where your water is inside. And then you have a lamp here. Okay, this is where your lamp is. All right, your lamp will shine light onto the pool of water below it. Okay, so as your dipper is moving up and down, it will form an interference pattern like the ones that you see on the diagram here. To properly see that interference pattern, you will normally put a piece of paper or white screen below the ripple tank. Okay, so the lamp will actually cast a shadow of the water waves onto the screen or paper below. Okay, that one is what you see as this one here. Okay, so notice that little black thingy here is actually the shadow that is being cast onto the screen, that is being cast onto the paper. All right, even if you don't cast a shadow below to see the interference pattern, you can actually just see on the water surface itself. Okay, so but casting a shadow onto a screen below actually makes the interference pattern clearer to see. Okay, even if you don't cast a shadow using a lamp, you can still see on the water surface, just that it's not as clear. All right, so this is ripple tank using water. Okay, so all these little statements that you see here on the next page is actually a reproduction of whatever I just mentioned. Okay, those spherical dippers are supported by vibrating bars so that they produce waves of the same frequency which spread out from each dipper. This ensures coherence. Okay, so The dippers are connected to the same vibrating bar, which is this one, which is connected to the same motor or the same lamp. This is to ensure that they produce waves of the same frequency. So if you see that you are producing waves of the same frequency, this is coherence. You are making sure the waves have constant phase difference. Okay. As the waves spread out from each dipper, the waves overlap with each other to produce a new resultant wave according to the principle of superposition. Okay, so the resultant pattern of waves is described by regions of large amplitude and zero amplitude, which can be explained as follows. So I mentioned to you that there will be a region where you have constructive interference. In those regions, the waves are always meeting in phase. Crest meets crest, trough meets trough. Here, what will happen is that you're getting a large amplitude wave. Okay, so this occurs along lines labeled C in the diagram, symmetrical about the center line between the dippers. The center line itself is a region of constructive interference. Now the center line is referring to this one here. If you look at the diagram, the center line is this one. It's the line in between the two dippers. Okay, so the center line itself will always be a region of constructive interference because the waves always meet in phase. Okay. Now, for disruptive interference, what we'll say is that there will similarly be regions where two sets of waves are always out of phase. For example, when crest meets with a trough. In these cases, disruptive interference occurs, causing almost complete cancellation, and the water will become in these places. This will always occur along the lines labeled D in the diagram, okay, between the regions of the constructive interference. All right. So that is for this. Along region of constructive interference, the water surface is still rising and falling at the same frequency as the individual waves, but with greater amplitude. Okay. The alternating pattern of the constructive and destructive regions is known as your interference pattern. So just now I mentioned to you, this little thing that you see here, where your constructive and destructive is your interference pattern. Okay, so total energy of the system here will always remain the same. Okay, because whatever energy that's lost in the calm regions, the calm region is the region of destructive interference. There are no waves. So no waves means no energy. It seems like energy has been seemingly lost here, but that energy is actually being diverted to somewhere else. It's actually being diverted to the area where constructive interference occurs. So your total energy of your system remains the same. Okay, so this is destructive so this is ripple tank experiment. Okay, maybe we better just do one question just to reinforce what we just learned. Okay, ripple tank. Let me just, can you guys just go to the book sheet? It'll be page 93, I think. Yeah. Okay, have a look at page 93 for ripple tank. Okay. So for page 93, you have a ripple tank that is used to demonstrate the interference of water waves. Okay. Two dippers D1 and D2 produce coherent waves that have circular wave fronts as illustrated in figure 5.1. Okay. This is two source interference because you only have two sources producing the wave, D1 and D2. Okay. So the lines in the diagram represents the crest. The waves have wavelength of 6 centimeter. One condition that is required for observable interference pattern is that the waves must be coherent. Okay, so describe how the apparatus can be arranged to ensure that the waves from the dippers are coherent. Okay, so when you want something to be coherent, you want them to have the same frequency. So one way of ensuring that they have the same frequency is to connect them to the same vibrator. In this case here, it was mentioned that you connect the dippers to the same vibrating bar. So that in this case here, if I make a diagram here for you, if this is your vibrating bar connected to which is connected to the two dippers, if your vibrating bar is vibrating with a frequency of 10 Hertz, obviously your dippers that are connected to the vibrating bar will also be oscillating at the same frequency of 10 Hertz. Okay, so this is the one thing, this is one of the reasons why we connect the two dippers to the same vibrating bar. All right, it's so that whatever frequency that the vibrating bar is oscillating at, the dippers would also be having that same frequency, exactly the same. This way, you would have coherence. Okay, so this one, let me just open up the answer for you. This is November 19, P21. Is it P21? Oh yeah, P21. Okay, so one of the things you will do is that you connect it to the same vibrator, same motor, or same vibrating bar. Okay. The vibrating bar in turn is connected to the same vibrator or motor actually. It's connected to the same vibrator or motor. Okay. So ensure that the dippers are connected to the same vibrator or motor or vibrating bar. Those would be okay. All right. Okay. So this is how you ensure coherence. You ensure that they are connected to the same vibrator or motor. Okay, then the other one here is this. All right. So state one other condition that must be satisfied by the waves in order for the interference pattern to be observable. Okay. Now, the overlapping waves must have same amplitude. Okay, what do we actually mean by this? Now, if I refer back to the little diagram just now in the notes, just now I mentioned to you your interference pattern is this one, right? Maybe I just draw a simple diagram here. I mentioned that your interference pattern is this series of lines where you have constructive and destructive. I mentioned that it's something like this. All right, this is where you always have the constructive. And then this is where you have the destructive. Okay, this is where you have the destructive. Okay, so now think of it this way. If I told you that the region of constructive interference has an amplitude of say 5 centimeter, and then the region of destructive interference has an amplitude of 0 centimeter, this one you can say that there is a very clear difference between constructive and destructive. Therefore, pattern is clear, right? I think they call it clear just now. Oh, sorry, pattern is observable, clearly observable. I just write it here. Okay, it's clearly observable. Okay, because you see here, when you're talking about the regions of constructive and destructive, constructive, the waves always have an amplitude of 5 centimeter, but where you have destructive, the amplitude is 0. So you can see that there's a very large difference between those two regions. The pattern will be clearly observable. But what if I told you the distracting interference right now does not completely cancel off, giving you 0 centimeter. Instead, you are getting a wave of reduced intensity. Maybe the wave has a new amplitude of 4 centimeter. So now you see this one, when you are constructing interference, the amplitude is fine. When you're distracting interference, the amplitude is just slightly less. It's only 4 centimeter. So in cases like this one, you will see that there's very little difference between constructive and destructive. Okay, very little difference between constructive and destructive. Therefore, not clearly observable. Okay, because you see, if you compare 5 centimeter to 0 centimeter for constructive and destructive, this one you can see a very clear observable pattern. But you compare 5 centimeter versus 4 centimeter for constructive and destructive, this one is not clearly observable. You can't see the difference there. Okay, so what caused the destructive interference to have an amplitude not being 0 here in the first place? So the reason for that could be because the waves were not having the same amplitude in the first place. Remember that time in the last lesson I mentioned to you, for destructive interference do not necessarily result in zero amplitude. They only result in zero amplitude when the amplitudes are equal in the first place. So if you look at page 2, this little diagram here, this one, the waves are meeting out of phase, okay? And they have exactly the same amplitude. This one is A, this one is negative A. So your resulting amplitude when they meet is just 0, okay? So here, when the amplitudes are equal, you would have 0 amplitude. So that time I mentioned this in the second page for you. If waves have the same amplitude and they meet destructively, the resulting amplitude is 0, okay? But if on the other hand, they don't have same amplitude when they meet destructively, you're not going to get complete cancellation. Okay, that one you can see under page 5 of your notes. Okay, so here it was mentioned that for amplitudes that are not equal, complete cancellation of waves don't occur during destructive interference. Since a small amplitude trough cannot completely cancel a large amplitude crest, you will get some sort of wave, but it's not as large as the individual waves before it. Okay, so let's just say right now you have 2 waves, the blue colored wave and this orange colored wave. They are meeting out of phase because you can clearly see that crest meets with a trough. This is destructive interference. So because they're not the same amplitude, they won't completely cancel off. You're still going to get some little bit remaining. All right, so you do this for the entire wave. This is the resulting waveform. Okay, so here you see you don't have complete cancellation. That is actually what caused your amplitude here for destructive interference to be at 4 centimeter. Okay, so back to that little question. State a condition that must be satisfied for the waves in order for interference pattern to be observable. So you can just say that the overlapping waves should have same amplitude. Okay, so when you have same amplitude, one of the main things that you can see is that you're going to have complete cancellation of the waves. Okay. When you have complete cancellation of the waves and you're getting 0 centimeter for the waves, for the amplitude, you can clearly see the difference between constructive and destructive. But if let's just say the waves amplitude are not equal, your destructive will not be exactly 0. You would have some value there. So when you compare with your constructive, you can't really see the difference. Okay, so that is for this. Overlapping waves must have same amplitude. Okay, now then after that you look at part B. Light from a lamp above the ripple tank shines through water onto a screen below the tank. Describe one way of seeing the illuminated pattern more clearly. Okay, so just now I mentioned to you, if you want to see the interference pattern more clearly, normally you will shine a light from a lamp so that the shadow of the interference pattern is projected onto the screen below the ripple tank. So right now, they're asking you another further improvement that you can make in order to see the pattern more clearly. Okay, so one thing that you can use to see the interference pattern more clearly is to use a stroboscope or strobe. Okay, so a stroboscope or strobe is actually a series of flashing light. Okay, so the lamp that you have here, you connect it to a stroboscope, it will cause the lamp to flash at regular time intervals. Okay, so when you use it at the correct frequency or the correct time interval, it will have the effect of freezing the pattern of the interference pattern form. What do I mean by that is something like this. Okay, this is what you would expect to see for the interference pattern formed by the ripple tank. Let's assume that this is the shadow image form. So right now you can see that if I just shine a light only, I will see this pattern, but the pattern is moving. Okay, I can clearly see the region of constructive and destructive interference, but I want to make it even better. I want to make it even clearer. So one way of doing that is to connect your lamp to a stroboscope. Okay, your stroboscope will cause the lamp to flash at regular time intervals. Okay, it will flash at regular time intervals, and if you use the correct frequency, it will freeze the pattern that you see. So when you use the stroboscope at a correct frequency, it will freeze the pattern. Something like this. Okay, you will see the waves there, but it doesn't seem to be moving. Okay, so that is what a stroboscope can do for you. If you use a stroboscope, the stroboscope has a series of flashing lights at regular time intervals. If you use the correct frequency, it will cause the pattern to somehow seemingly freeze. Okay, so this is how you see the pattern more clearly. Or any other means of strobe or freezing the pattern. It's just stroboscope or strobe, all right? Okay, so the last little thing that we need to do before I give you guys a short break is this. Now, look at part C. The speed of the waves is 0.4 meter per second. Calculate the period of the waves. You can just use V equals to F lambda. Frequency is actually 1 over T. Okay, now how do you get the wavelength in the first place? Recall that in this question, they mentioned this. The lines in the diagram represent the crest. The wavelength is 6 centimeter. So when they say the lines represent the crest, it's actually referring to these lines here. Okay. It's referring to these lines here. Okay. So this is one crest. This is also one crest. So the distance between adjacent crests is your wavelength. because you see, if you look at the waveform, distance between adjacent crests is actually your wavelength. Okay, so you know the wavelength already as 0.06. Yeah, actually you don't even need to refer to the diagram because they already told you the wavelength. But in the event that the question tells you that the distance between the lines or the distance between the crest is 6 centimeter, you should automatically relate it to wavelength. Okay, so you use the equation v equals to f lambda, sub everything in, you eventually get the period as 0.15 second. To recap a little of what we just learned, when you're talking about the ripple tank, we were interested in looking at the interference pattern caused by water waves. Okay, so that one is shown using a ripple tank. So when you're talking about the interference pattern, there will always be regions of constructive and destructive interference. All right, so this one, using the ripple tank, we show interference pattern using water waves. Okay, what about other different type of waves? Let's just say light waves or sound waves. Will we also get interference pattern similar to that of water waves? The answer is yes. If we use different types of waves like light waves or sound waves or even microwaves, we will still see interference pattern caused by two different sources. All right, so we will see the interference pattern, but the way we see the interference pattern, the way we detect the interference pattern will be different. Okay, for the water waves, it is easy for us to see the interference pattern where we have the constructive and destructive interference. All we needed to do was to shine a light onto the ripple tank, and then we will see the shadow of the interference pattern form below the ripple tank. But if we try to repeat the same thing using, say, light waves, let's just say right now we have source A and source B again. But this time, these two sources are producing light waves that are spreading outwards in a circular wavefront. Okay, we would expect to see constructive and destructive interference too, but can we shine a light onto the pattern to see the shadow of the light? It doesn't make sense, right? Whatever we are using here right now is already light in the first place. If we go and shine light onto the interference pattern, we cannot see the shadow of light. It is ridiculous. We can't see it. So how do we go and detect the interference pattern caused by light instead? All right. So to detect the interference pattern caused by light, we would have to use a different apparatus, a different method of seeing or detecting the interference pattern. So when it comes to showing the interference pattern or detecting the interference pattern caused by light waves, caused by two source interference pattern of light waves, we will use something called Young's double slit experiment. This is specifically for light waves. Okay, the previous one for ripple tank is for water waves. For light waves, we always use Young's double slit experiment. Okay, so interference effects can also be demonstrated by light using Young's double slit experiment. When coherent light is directed towards two slits, a series of equally spaced fringes or dots of light are seen on a screen placed behind the slits. The bright fringes with dark regions in between are referred to as interference fringes. Okay, so if you refer back to this little diagram here just now that I had, what we're essentially doing now here is this. I'm just going to reduce this little diagram here. What we do is that we shine light onto a piece of plate that has two slits. Okay, it looks like this. Okay, this is what we call a double slit because it has two slits. All right, we shine light onto a double slit. So each slit here in itself would act as a source of light. Because you see, when you shine light onto a double slit here, each of these slit will act as a source of light, a separate source of light. So when light hits this one, it will cause a new source of light, and it will spread out in circular wavefront. Then when light also hits this second slit, this acts as another second source of light. The light will diffract and it will spread out. Okay, remember in diffraction in the last lesson we mentioned that when a wave hits a opening or a slit, it will tend to spread out. So what's happening here is actually due to diffraction. Okay, so your light hits one slit, it produces a new source of light. It hits the second slit, it produces a new source of light. Okay, these are two separate sources, and the waves are actually spreading out. It's actually due to the effect of diffraction. Light hitting the slit causes the light to diffract, to spread out. Okay, so these two are considered to be two separate sources of light right now. Okay, so when the two sources of light, when the light waves from the two sources spread out, they will overlap at certain regions, just like the water waves. Okay, so certain regions will always be having constructive interference, certain regions will always be having destructive interference. Okay, so as I mentioned to you just now, you would have those regions of constructive and destructive, like the ones that are seen here. So where you see that you are going, where you have constructive interference, this part here is supposed to be bright. Okay, because the light waves overlap with another light wave, you're supposed to get another light that is brighter. But on the other hand, where your waves are interfering destructively, if the amplitude is equal, are the same, they should completely cancel off. So this part here should be dark. Okay, so the principle is still the same, like the water waves. You will still have regions of constructive and destructive interference, but because of the property of the waves, the property of the interference pattern will be slightly different. Okay, so constructive interference, you expect to see something that's very bright. Destructive interference, you expect to see something that is really dark. Now, if you want to see this pattern here, just now I mentioned to you, you cannot simply shine a light down onto the interference pattern to see a shadow. The moment you shine a light down, the bright light will be, if you shine the light down onto the interference pattern, you cannot produce a shadow from light. Okay, the light will be absorbed already by the lamp. So you can't see the interference pattern by shining a light onto the pattern and expecting to see a shadow. So the only way you can see that this interference pattern is by two ways. Either you place a screen, either you place a screen in the path of the interference pattern. So where the pattern hits the screen, it will form some sort of fringe. So where the constructive interference region hits the screen, you see a bright light here. Where the destructive interference region hits the screen, you don't see anything here. And then similarly, when the constructive interference region hits the screen again, you see another bright light. Where destructive interference region hits the screen, you see nothing. Okay, so you try to expand this across the whole screen, you're going to see something like this. Bright, and then dark, bright, and then dark. followed by bright again. So you see, this is also considered to be your interference pattern, but we call it interference fringes now, right? Sometimes we call it interference pattern, we call it interference fringes, all right? So rather than shining a light onto the interference pattern to see a shadow of the light, which we cannot do, instead we put a screen at the front so that the constructive region will form a bright fringe on the screen. The destructive region will not form anything on the screen. It's considered to be dark. Okay, that's why here we tell you, you will see, we tell you when you direct a light through slits, you see a series of equally spaced fringes or dots of light on the screen placed behind the slits. Okay, so what you're seeing here is the light, it hits the double slit, and then after that, this is the screen. On the screen, you see a series of bright dots and nothing in between the bright dots. This is your interference fringes. The bright fringes are the regions where light waves from the two slits arrive in phase where constructive interference occurs. The dark regions are the regions where the light waves arrive out of phase with each other, where destructive interference occurs. Okay, so this is one way of looking at the interference pattern. Now, another way of looking at the interference pattern could also be like this. You can conduct this experiment in a completely dark room, and you'll be able to see these beams of light. Okay, so you have to do this experiment in a very dark room, then you'll be able to see these beams of light here. Okay, these beams of light that you see here is actually these regions of constructive interference. Okay, so remember just now when the waves overlap, you were supposed to have regions of constructive and destructive. So rather than shining light onto the interference pattern and expecting to see a shadow, why not you just make the room completely dark? If you make the room completely dark, you ought to see these beams of light. The beams of light that you see here is actually the regions of your constructive interference. Okay, but if you cannot make your room really, really dark to be able to see those beams of light, what you could do is you place a screen at the front. So where the constructive region, when the constructive region hits the screen, you see a bright dot. When the destructive region hits the screen, you see nothing. It's considered to be dark. Okay, so this is how you see the interference pattern caused by light. All right, so this is the diagram simplified already for you. Okay, so a narrow slit S0 is placed in front of the monocommitted light source, while double slit S1 and S2 is held parallel to in front of the single slit. The narrow slit here provides coherent light waves by diffracting the passing light so that it arrives in phase at the double slit. This ensures that the double slits behave as two coherent light sources. Okay, so these are your two sources. Okay, we are talking about two source interference patterns. So these are your two sources. So you need to make sure that these two sources are coherent. The waves that they produce have the same frequency, have the same phase difference. One of the ways in doing that is to use a single slit before you shine light through it. Okay, so the single slit here ensures that whatever light you shine to the double slit is coherent. Put it this way now. The narrow slit provides coherent light waves by diffracting passing light so they arise in phase at double slit. And this one, the single slit, is to ensure coherence at double slit. Okay, so you shine a light, you place a single slit in front of it first, let the light pass through the single slit like this. Okay, like this. It passes through to the double slit, and then when it passes through a double slit, it becomes two sources like this. Okay, so the single slit is to ensure coherence. The double slit is to make sure you have two sources. Okay, to produce two sources of light. Okay, those are the purpose of the slits. The single slit before is to ensure coherence of the double slit later. The double slit is to give you two sources of light. All right. So in the interference regions where S1 and S2 overlap, there are regions of constructive and destructive interference, similar to the waterways in the ripple tank. Regions of constructive interference appear as bright beams of light that have maximum intensity. Regions of destructive interference have zero intensity or no brightness. They appear to be dark. Okay. So when a screen is placed in the path of the light beams, an interference pattern of bright and dark fringes is observed. Okay, when we say the pattern of bright and dark fringes, it's referring to what we see here. We are always going to see bright, dark, bright, dark, bright, dark, bright, dark. This is what we call the interference fringes. Okay, so these little lines that you see here all represent the regions of constructive and destructive interference. The red colored line represents constructive interference. The dark colored lines represent destructive interference, which in turn gives you your bright and dark fringes respectively. Okay, so usually when you want to do this experiment, we will tend to use a monochromatic light beam. Okay, so that we only see a single color. Okay, so when we talk about monochromatic light, yeah, I better just mention this. Monochromatic light source monochromatic light has only a single wavelength. I.e., only a single color. All right. Usually, when we do a double slit experiment to see the interference pattern of light, we tend to use monochromatic light. Monochromatic light means you have single wavelength only for the light. That means you're dealing with only a single color. If you are not using monochromatic light, you use white lamp, for example, like the lamp that you see in your room right now, the color is white, but it's not monochromatic. Okay, it has many different colors, many different wavelengths of light inside that combine to give you white light. Okay, so specifically when you do this experiment, ideally we want monochromatic light so that we're dealing only with a single color. Okay, so that part is okay. So here, if you look back at page 9, usually when you want to use your double slit experiment to see the interference pattern of light, you would tend to use laser, okay? Because the laser, for a laser, the light beam is more concentrated. Okay, it makes the fringes very clear, all right? If you use white light, as I mentioned to you, there will always be a range of wavelength presence in the light. It is not monochromatic, okay? So different wavelengths will form fringes at different points across the screen, smearing them out so that they are not as clear. Another thing that I should mention here is this. If you have different wavelengths or different colors, okay, different wavelengths will appear as different colors on different points on the screen. Therefore, smearing the interference pattern. Okay. All right. So If you use white light, there will always be a range of wavelengths present. Okay, the different wavelengths will form fringes at different points across the screen, smearing out the image. Okay, because like let's just say if you have, let's just say you use red light, you expect to see only this. Let me give you an example. Let's just say this is the screen. If you use red light only, you will see something like this. Okay, this is your interference fringes. All right, but if let's just say you have white light, if let's just say you're using white light, okay, if you're using white light, let's just say I tell you got red, got blue, got orange now. Let's just say these three colors now. I know there are 7 colors, but let's just say I tell you I only consider the 3 colors. So red would be somewhere here like this. Blue would be somewhere near the red. It won't be exactly at where red is, at different locations. Like this. So maybe I should do it like this. You know, this is the center one. This. Okay, blue is like this. Then orange would also be somewhere near, but not exactly at where red or orange or red or blue is. Maybe it's somewhere here like this. Anyway, sorry. Okay. So this is what we call as smearing, right? Because the colors seem to be mixed. All right. So different wavelengths, different colors at different points on the screen. So you will smear the interference pattern as opposed to you using just a single wavelength or monochromatic light. Okay, so if you have to use a white light, no choice because you don't have, say, a laser, but you want to have monochromatic light. What you can do is that you can use a color filter. All right, what you can do is that you can use a color filter. So say for example, you have your white light, which is here, then this is your white light. You place a single slit here to ensure that your light is coherent afterwards. Before you put your single slit, what you do is that you put a color filter. This one here is your monochromatic filter. Okay. This one thin line here is your monochromatic filter or your color filter. Okay. So let's just say this is white light. If you put a color filter, let's just say it's a red color filter, it will only allow red color to pass through. If let's just say you use blue color filter, it will only allow blue color to pass through. The rest of the colors are filtered out. Okay, so if you have to make a white light into monochromatic light, you use a monochromatic filter. Okay, then you place a single slit to ensure coherence of your waves. All right. Okay, so if let's say you're using white light again, let me just go back to the original discussion. If you're using white light, you expect to see those interference fringes form. Okay, but specifically what we'll tell you is that the central fringe will be white because all the wavelengths are in phase here. Let's just say that this is the central fringe now. Okay, the one at the center, the pattern that's at the center, which is this one. Okay, so specifically the one at the center, all the colors will always overlap at exactly the same point. Okay, all the colors or wavelength will overlap in phase. Will overlap exactly in phase. Therefore, the fringe is white in color. It's because all the colors overlap at exactly the same point, they will combine back to give you white. Okay, let's just say that this one was the white color with the central fringe. If you use white light, you're going to see the same white light here. But the rest of it won't be white because you see the other colors seem to be at different positions. It's being smeared out. Okay, right? So other fringes show rainbow color effects as different wavelengths interfere constructively at different points. This is what I was talking about here. Sometimes we call them as being smeared out, or sometimes we will tell you, you see some sort of rainbow colored effects because the wavelengths are at different points, the colors are at different points. Okay, right. So that one is for double slit.